Module 7. Circles with segments. Arc lengths. As mentioned in Module 6, if theta is the central angle of an arc, the r is the radius of the circle, then the arc length is given by r times theta, provided that theta is measured in radians. Consider this example. We're given the inscribed angle in radians and the radius. To find the length of the bolded arc segment, we need the central angle and the radius. The central angle is the angle measurement of the arc. By the inscribed angle theorem, as we discussed in Lecture 6, we conclude that the angle measurement of the arc is 2/5 times pi. From here it follows that the arc length of the arc is 3 times 2/5 times pi, or 6/5 times pi. Lengths between chords. If two chords intersect in a circle, they divide themselves into two segments each. The angle between x and a in this case is equal to the angle between c and y, since those angles are inscribed by a common arc, as we discussed in the last module. In a similar way, the angle between x and d is equal to the angle between b and y. Furthermore, the angle in the middle of the picture is formed by two intersecting lines. Recall that opposite angles are equal, they're vertical angles, and so the two triangles inside all have equal angles. Thus, it follows that they're proportional. So the triplet XAD is proportional to YCB. Thus, x over y equals a over c, which equals d over b. For our purposes, we care about the equality a over c equals d over b, and cross-multiplying we get a times b equals c times d. Thus we have proved that the product of the segments intersecting chords are equal. Consider this problem. The products of the segments of one chord is 8 times 3, which is 24. Thus, the product of segments of the other chord is 6 times x, which is 6x. Thus, 6x equals 24, and from there we get x equals 4. Lengths of intersecting tangents. Suppose that from a single point, two common tangents are drawn towards a circle. We draw two radii from the circle, or in the circle, from the center to the point of intersection between the two tangent lines, and then we can draw a line from the center to the point from whence the two tangents came. The angle between r and x and the angle between r and y are right angles. It may seem obvious from the picture, but at the end of this module we'll explain why. As we have two right angles, and L in this case is the hypotenuse, which is the side opposite the right angles, we have from the Pythagorean theorem r squared plus y squared equals L squared, and r squared plus x squared equals L squared. Canceling the r squared from both sides, we get x squared equals y squared, and so x equals y. This proves to us that common tangents to a circle all have the same length. Length of intersecting tangent with a secant. The relationship between the length of a tangent with a secant is that of the square of the length of the tangent, or a squared in our diagram, is equal to the product of the total length of the secant, b plus c, with its outer segment, c. That is, a squared equals c times b plus c. It's very important not to use the product of the two segments in the secant. Rather, it's the product of the full secant with only its outer segment. We can find a relationship between the secant length segments from this by first drawing a tangent line from the point. Now, each of these two secants together with the tangent satisfies the equations a times a plus b equals e squared, and c times c plus d equals e squared. It thus follows that a times a plus b equals c times c plus d. Thus we can say that two intersecting secants have equal products of their lengths with their outer segments.